as the leader of the Pavilion Lake Research Project, which has a lot of astrobiological implications. So take it away, Darlene.
So what I'm here to talk about, as Adrian mentioned, is the Pavilion Lake Research Project. And this is a multidisciplinary project that's been going on for some years now, and it really brings together sort of the confluence between science and exploration. And I'm going to take you through the entire story of the Pavilion Lake Research Project. I know we have a broad audience here today, and so I'll walk you through the story as to how we got to where we are today in terms of the size and the extent and the activities of our project, and also tell you about the science that we've been doing, and also how this is relevant to human exploration on the moon and Mars. And that's where this title of the talk comes to in terms of the deep dive towards the moon and Mars. Everything we do is at Pavilion Lake requires us to basically get wet. So we either do science from a boat, in many circumstances we're underwater doing scuba, and then over the last couple of years we've brought in a new technology to help us attain our science goals, and that is this submersible here called the Deep Worker Submersible that I'll talk to you about as the conversation goes along. So before we started, I had a question: are all of these photographs from Pavilion Lake? And the answer is yes, none of them are doctored. It is indeed this beautiful and this dynamic. And the reason why we're at Pavilion Lake in terms of the science is because of this. These are microbialites, which are carbonate structures generated by microbes, microbial, and then ite being the rock component. And so it's that interaction, understanding their construct, understanding whether or not any of the signatures of life that we may detect on the surface of these rocks is actually being preserved within the rocks. Those kinds of questions is why we're there. But then, as I said, all of the mechanisms that we use to get at that science, to collect these samples, the organizational kind of level, those types of details and lessons learned are what are relevant when it comes to understanding the way we should do science, or we can do science on other planets. So I love this project, and I love it really because of the story and how it sort of came about. Now, this is a photograph of Pavilion Lake, which is in British Columbia, Canada. So if you go up to Vancouver and then you drive about 4.5 hours eastbound from Vancouver up into the semi-arid zone of that province, you'll come to Pavilion Lake. For all intents and purposes, it looks like a very innocuous, very beautiful recreational Canadian lake, and that's exactly what it is. And for years, nobody actually knew that if you were to put your head underwater with some scuba gear, you would see a whole new world, which is this image here with the scuba diver interacting with the microbialites. The mechanism for discovery was this. There were a lot of really sort of hardcore recreational divers in British Columbia, Canada, that kept talking about these freshwater corals in Pavilion Lake. And so word got out that this was there in this particular lake, and the recreational divers were kind of using it as a mechanism to vet each other with, because the carbonate flour throughout the lake is very, very fine. All you have to do is fin in just the wrong way, and the next thing you know, you've created a bit of a snow globe around you. I've done it many times and won our special snow award for bad finning. But it really is kind of a test of your capacity to be buoyant and be very still and be a very choreographed scuba diver. And so for years, that's what this lake was. Oh, come check out these interesting corals, freshwater corals. But eventually there was a man, Harry Bohm, who kind of put it together. Like, there must be something very interesting about these freshwater coral. There must be some relevance outside of this sort of macho vetting. And so eventually he started talking to people who eventually got the word down to this part of the world, to Norm Pace and to Chris McKay, and they realized that they had something very interesting in front of them. And they mounted a small expedition at the end of the 90s that resulted in a paper in Nature in 2000. And what this paper discussed was the very interesting shapes and forms, morphologies of microbialites in this particular lake, and the relevance of this site as well to understanding early Earth systems when, of course, there were microbialites or stromatolites, which many of you probably heard about throughout our shallow seas. So once again, just to give you some situational awareness, there is Vancouver, and you can easily get to this lake by car. It's very easy to do science from the standpoint that it's not as remote as some other interesting sites that I've been to. So the lake is this one here. It's the long, skinny one in the top of the image. That is Pavilion Lake. It's almost 6 kilometers long. And there are 3 basins associated with this lake. The south here, the central, and then a north. And I'll show you a three-dimensional schematic in a few slides that will basically give you an understanding of this lake if you were to drain all the water out and kind of walk your way through Pavilion Lake. The lake is circumneutral. It's about a pH of 8.4, 8.3. And this lake is groundwater fed, and it's very, very clear. These SETI depths give you a sense of water clarity, or the transmissivity of light through the water. And 15 meters is very, very clear, just to give you kind of a conceptual understanding. This we actually think is one of the interesting components that's actually impacting the microbialites actually being in this lake here and not in any of the other adjacent lakes, such as these two, which are further south of Pavilion Lake. The other thing about this area is that we're within a very steep canyon called Marble Canyon. So there's karst hydrology that dominates the area. And of course, the last point on this slide is that we now know that this lake doesn't just have a few areas that are replete with microbialites, but rather the entire lake is filled with microbialites of varying size. So to sort of set up the background, what is a microbialite? The classic definition of a microbialite is that it's an organosedimentary deposit. And this is accreted or formed as a consequence of benthic microbial community trapping and binding, or binding detrital sediment and or forming the locus of mineral precipitation. Now, in this definition, the key component that we're interested in investigating is this role of the microbial community. So we know that there are a bunch of different microbes living together, but what it is that each one of them are doing and how that's contributing overall to the construct of these carbonates and their overall shape and size is what we're trying to do from a variety of different angles. And I'll use some terms throughout this talk. Stromatolite, indicating a laminated or sort of layered fabric of microbialite. Thrombolite, which is a non-laminated clotted fabric, so this internal fabric here that you see in this cross-section, bless you, of microbialite. And then also there's the term dendrolite, which I probably won't say, but if you ever hear it again now, you'll know it's this branching fabric that sometimes is associated with microbialites as well. And so the thing is, in the rock record, this is an image here, believe in of an Archean stromatolite, is that without the minerals, a microbialite is just a microbial mat. So what is it that is allowing for the microbes to eventually construct this particular shape and size? This is almost 2 meters in height, so it's very large, is what we're trying to understand. Because, for example, in the Pavilion Lake in the Pavilion Lake area, if you just drive 20 kilometers away, there are lots of very interesting hypersaline ponds. And within those ponds, there are very thick mats that have interesting laminations or layers to them, and there are carbonate precipitates intertwined between those layers of mat. But none of them are actually building up to this construct. So we know that there are sort of end members that allow eventually for these types of rocks to be built. And that's another component that we're trying to investigate and tease apart. So in Pavilion Lake, we know that from the scuba diving we've done, from the submersible transects that we've done throughout the lake, that there are sort of trends and delineations by depth in terms of the shape and the size of the microbialites. And what those correspond to is what we've been investigating. So in the shallows, between about 5 and 15 meters, so multiply by 3 if you're thinking in feet, we find these microbialites that we've called in the past sort of crunchy, like cauliflower type microbialites. We'll use a lot of the terminology that we've used over the years. You'd think that we were all vegetarians because we call that the cauliflower, the artichoke. And well, various names have come up with those chimneys, but we've landed with chimneys. Somebody called them corn on the cob, but we'll just avoid that for now. But these rounded structures, which are very friable, very fragile, and difficult to sample actually underwater, are found in the shallows. And then descending deeper into the lake, we start to see the microbialites change in size. As I said, this is probably about a meter from end to end here, and they get much more consolidated. The other interesting thing is that the surface of these sort of soccer or just slightly larger than soccer ball size structures are coated with tufts or nodules, sort of rounded bulbs that now that we've teased apart, and I'll show you in a few slides, we can certainly see the cyanobacteria forming these rounded nodules or tufts. And they are also associated on the surface of these deeper structures. But as we start to descend deeper into the lake itself, we notice that those tufts seem to disappear and the structures get much smoother and they take on this sort of artichoke shape. So we have these leaves that are anastomosing, or literally just kind of the external shape of them are sort of coming together in these very interesting forms. And this particular structure right here, this one artichoke, is a mega artichoke, is about 2 meters by 2 meters. So it's very large. And just qualitatively, they're incredible to come upon as you're diving in this lake, whether you're in a sub or doing scuba. And so, as I mentioned, as a result of that early expedition, a paper came out in 2000 that sort of set the stage and described these different depth changes and the associated morphologies of microbialites in Pavilion Lake. But there were a lot of other questions that were outstanding as a consequence of that particular paper. And one of the questions that was outstanding was really the capacity for us to understand the interaction between biological, chemical, and physical factors in eventually affecting the larger morphologies of, that we see in the lake there. So relating this back to some of the outstanding questions in the literature, how do microbialites form? Are there abiotic or biotic forces at play? What are the biosignatures, if any, that are being left behind in these rocks? And what are controlling the larger shapes and sizes of the microbialites? These are all outstanding questions that we realized at Pavilion Lake, given that there is a modern system there, we could go in and tackle. And so this is as I mentioned, a system that we now know is still seeing active carbonate precipitation, is easy to get to. We can go there and seasonally and do long-term studies as well. And then this component here has come in recently. This bullet point is kind of a new addition, and that we realized sort of halfway through doing the research that, in fact, the mechanisms, as I mentioned, that we use to explore in this lake, because it is underwater, because it is hostile to us being there, has direct application to actually doing research on other planets and, of course, on the moon. So what I'm going to do now is I've populated this triangle of hope, is what I'll call it, with different images. And I'll take you through some of the research that we've been doing to take a look at this triangulation and this understanding of microbialite morphogenesis. And let me just start off here. The thing I wanted to start with is that this has really been a labor of love. And it started with me coming to Ames to postdoc and to spend some of my postdoctoral time at this lake. And this was in late 2004, and really the major activity started up in 2005. But what is very interesting is that when we first started this project, it was small, and we didn't have a camp cook, and we just called ourselves a little trip. But now we define ourselves as a project, I think largely as a consequence of the fact that we have a camp cook. So that's a loose definition, but now I no longer make the spaghetti, which is brilliant. So it's grown. In 2005, we started to add some new faces as a consequence very much of the fact that the lake is interesting. It's not hard to sell in terms of the science, and now in terms of the exploration. And then in 2006, that is me completely knocked up, about 8.5 months pregnant in the field, and out there. In 2006, the major event is that we got a lot of new graduate students who have totally become the workhorse of the project. I think we have about 6 graduate students who are doing their PhDs or just at the tail end of their time, putting their time in on their PhDs, and several other graduate and undergraduate students. And then in 2007, we grew again, and it was still a diving-based project. And at this stage, we added our camp cook, I think either in 2006 or 2007, but that made a big difference and formalized this as a project. And then in 2008, we grew substantially as a consequence of the submersibles coming into our lives. And so the other component that we added to our lives were astronauts. This is Dave Williams here. This is Mike Gernhardt over there. And they have embedded themselves with our project, not as VIPs or just kind of superficial visitors. They are there, they do the dishes, they get involved with doing scuba dives, submersible dives, And the other thing is that they're helping us with the science. And Mike has gone off in particular and just formulated his own team to actually really ramp up in the exploration and science side of things, which I'll talk about in a little bit. This is our family picture from 2009 and our very intrepid and lovely cook over there in the bottom corner, who's made a big difference to our lives. The other thing that's happened this year is we've had more astronauts join us. This is a brand new Canadian Space Agency astronaut, Jeremy Hansen, who joined us, and in the top right over there is Ricky as well. And then you see a lot of young faces. Our average age is about 28 years old. Those are all the students that really, as I mentioned, are the backbone of this project. So before I get into teasing out that triangle, I want to bring up a set of guiding principles, because I find that at the end of every talk, what I get asked is, why did you guys bring in the subs? Why did you decide to do scuba, and so forth? And I wanted to just let you know sort of our decision-making protocol, I guess, that we've instituted for many years now. And this is that everything that we do, we try and make sure is, first of all, safe. So this is in our order of priority. Is environmentally friendly to the land that we're trying to study. Advances the science that we're trying to do, and last but not least, advances human exploration. And so nothing that we'll do, we'll never put a piece of technology in the water that might advance human exploration that isn't safe, because that counteracts the entire kind of longevity, really, we think, of our project. So one of the first things that I want to talk to you about is this here, the interaction between the chemical and the physical, and understanding the limnological relationships and trends that really are setting Pavilion Lake seemingly apart from the other lakes in the area and allowing it to harbor these microbialites. So what we've been doing is, over the years, we've laid transects throughout different parts of the lakes, and in those transects we've collected groundwater. We've looked at pore water, which is what you see up in the top here. These are pore water peepers. We've collected water from throughout the lake itself, and also installed thermistors, which allow us to look at annual temperature trends as well. We've also taken a look at the interaction of the geology with the groundwater itself. Pavilion is rather interesting in that this is, once again, Pavilion Lake here, and it actually contacts 3 different bedrock types in the top. This granitic bedrock over here. This is all siliciclastic material, and then this green is actually the Marble Canyon area here. So all of that marble and other carbonate rocks. And what we found is that when you just look at the chemistry of Pavilion Lake itself, that it is set apart when you, from the other lakes that we sampled. And we sampled quite a few other lakes and ponds in the area, one of which we made the discovery also has microbialites in it, although they look very different, and that's kind of a separate talk altogether. But some interesting points of comparison between those 2 sites. One thing we found with Pavilion, or a few things we found, is that it has the highest mean conductivity and the highest mean sodium levels. Not very high. You know, it's not a hypersaline environment like some other sites that have microbialites are, but it actually does have higher sodium concentration than other sites in the area. And it had the highest mean DIC and lowest carbonate as well, concentrations. The one thing that we thought was pretty neat about this lake as well is that it had the lowest nutrient concentrations when you look at the mean total phosphorus. And the values that were associated with this lake indicate that it's ultra-oligotrophic. And we think that that might actually be an interesting factor, which is sort of balancing the overall ecosystem of this lake. And the other sort of notable component, or physical component and limnological component of this lake, is that it has very low sedimentation rates in terms of what's falling out of the water column itself. We have not looked at any of the sort of benthic sediment loading that could be happening as well in the lake, and we plan on doing that. But in terms of what's actually raining out of the water column, we thought that a lot of that carbonate flower was perhaps a seasonal event of carbonate generation, but we in fact discovered over 2 years of monitoring that this is not the case. In fact, there's a very negligible amount of sediment that's accumulated annually in the lake itself from the water column activities, either from organic or inorganic components. And in the lake that is nearby, that also has microbialites in it, which look very different, that lake has in fact 9 times more sedimentation than Pavilion Lake. So there is that slight difference, or that difference between Pavilion and the others in that respect. The other thing about Pavilion is that we know it's groundwater fed. You can see that there are sort of areas, there are marl benches or these beaches of carbonate flour which indicate regions where there is groundwater coming in. This lake so it's groundwater fed. So we went looking for groundwater input points so we could collect from those particular areas and also take a look at that interaction between groundwater and the ambient lake water. And what we found is that we couldn't find anything. It was really a pain until last year. And so what we found from our find last year and also from our search is that the groundwater must be coming in a very low diffuse flow. And in fact, there is a higher salinity and conductivity value associated with the deeper portions of Pavilion Lake where we suspect their groundwater is coming in. And last year, and we confirmed it this year, we found some areas where you can actually see the groundwater coming in the southern portion of Pavilion Lake. And also there are several other limnological trends, which I think are coming up in this next, in a few more slides. Let me just jump forward here. That show us that in fact, the groundwater is moving from south to north. And now it's completely jammed up. Just go back here. So this is the three-dimensional map that I spoke to you about earlier on in the presentation that's been generated by folks from the University of British Columbia and the University of Delaware using that autonomous underwater vehicle, which is called Gavia. It literally looks like a torpedo. And it has been running transects up and down Pavilion Lake and using sonar and then to map out the lake. And then through a software program called Fledermaus, this map was generated. And it gives you a really nice three-dimensional look. Of course, there's some exaggeration here in terms of the internal topography of Pavilion Lake. And this is the southern basin, and where we found the springs coming in was at this end here. And what's interesting is that there seems to be a freshening of water from our water collections as you go from the south to the north. And so there's this hydrological pull of groundwater in this particular movement here. And so we've not actually found any other distinct springs anywhere else in the lake, but we know that the water is moving in that general direction. And what's interesting is that the southern basin, just qualitatively, is very diverse and rich with macroalgae, with kind of pools of green filamentous algae. The microbialites are very large in this section of the lake here, which begs the question as to whether or not those nutrient inputs are making a difference and whether or not this development here is richer than the rest of the lake. Let me just back up. I want to tell you a couple more things here. So coming back to this question of groundwater, a couple of collaborators from McMaster University in Canada have been trying to understand what is the input of groundwater into Pavilion Lake. What kind of percentages can we actually constrain in terms of the amount of groundwater that's coming into the lake? So this does not address the issue in terms of what the groundwater does, because we know that groundwater has higher concentrations of things like calcium and nutrients compared to the ambient lake water. So it's not dealing with that, but rather trying to get an understanding of what kind of percentage we can calculate using mass balance calculations to constrain, I guess, the percentages coming into the lake. So they used stable and also radiogenic carbon isotopes to look at the component of groundwater coming in. And there are really two sources of groundwater into the lake itself. There's the local groundwater, which is coming down, we think, from the hills, percolating through all that limestone and marble and coming into the lake itself. And then there's the regional groundwater, which is flowing from a farther distance away, and which, looking at the C14 values, interestingly enough, this groundwater is near, what's considered to be dead. So that provided an interesting kind of end member in their calculations. And what all these graphs show is that the net result is a couple things that are interesting. The groundwater inputs using the C13 and the C14 values was constrained to be between 7 and 9% of the contributed carbon source into the ambient lake water itself. And the lake water C14 values are minus 45 per mil. And they also used what's called PLFA, a phospholipid fatty acid analysis, which is gives you an indication of the biomass, the living biomass on the surface here. And they used C14 as well to look at the carbon contributions into that living biomass. And what they found is that the values they were getting from that living biomass and what compared to the lake itself were very similar. So that tells you that, or gives you a suggestion, in fact, that the carbon source that's being utilized by those surface communities is coming from the ambient lake water rather than any of the groundwater sources. And one thing I will add is that deeper into the lake itself, some of these PLFA C14 values did change. And in fact, they actually became more depleted, indicating that there might be some incorporation of this deeper, of some of that groundwater as well into their cellular construct. So these are all coming together really to suggest to us that there is on the surface anyways, a strong indication that the biology there is using the ambient lake water as its carbon source, and that the groundwater may not be as big a component in terms of its influence on the microbialites themselves. But there's still many outstanding questions related to that. And the other relationship we wanted to look at was between the biological and the chemical. So as I mentioned, there have been several different kind of sampling runs that have been made using scuba, and also we've done some collections down deep using the submersibles as well. And we've targeted all of these different morphotypes or shapes and sizes of microbialites through our study. And so some of the things we've been trying to find out is the distribution of photosynthetic elements within the microbialite structure itself. Is there only photosynthesis happening at the top and perhaps not at the bottom at all? What are the relative rates of activity and the role in calcification? What is the community composition and the variability when it comes to the surface communities anyways? And what is the link between the photosynthetic community structure and activity and the gross morphological shape? So bringing that all back to what is the influence of those communities on the generation of those different shapes and sizes. And then the last question, which we're trying to look at going forward, is whether or not there are any biosignatures that are actually being preserved within the carbonates themselves. So I've been showing you those images of the structures from a kind of a gross morphological standpoint. But if you just put them under a microscope, even a stereo microscope, and these are some images that were taken close up actually in situ in the lake itself by a diver, you see, as I mentioned, a lot of these nodules or tufts associated with the surface of the carbonate structures. And they're dominated by these pink and green tufts. If you tease them apart or actually zoom in on them, what you see is this image here, which it is 1,000 microns right here of this tuft. And it's, whenever I take a look at this picture, I'm reminded, I showed this picture for some reason to a friend who's a nurse, and she looked at it, and the first thing she said was, "That's disgusting, it looks like tongue cancer," which, it's just, I feel like it's one of those images, you take what you want away from it. But getting closer and closer into this particular tuft, you start to see the calcite minerals intertwined, or rather these filamentous structures here intertwined with the calcite minerals. Thank you so much. And by pulling them apart, you can really see that the minerals are, and the filamentous organisms as well, are completely balled up into these particular tufts. And so one of the things we're going to be working on with a collaborator that's just joined us is just doing simple like microscopy and really getting down our taxonomy of what's actually living there. Because the other thing is that if you take one of the green tufts and cut it in half, you see these kind of what we're calling microstromatolitic laminations, or these micro-laminations where you get green and then the calcite minerals and green and the calcite minerals again. And this was pretty cool for us to see. And so, as I mentioned, the collaborators at McMaster University actually looked within these structures themselves into these stromatolitic or microstromatolitic formations and did some microelectrode probing. And what they found is that there's oxygen supersaturation in the green areas here, which is indicative of active photosynthesis. And the other thing that they did then is they took a look at the calcite precipitates and their C13 values and compared those to the expected C13 values for the carbonate minerals if we were those are the expected equilibrium carbonate C13 values. And they did a comparison and found that there was indeed an enrichment up to about 3 per mil. So once again, indicating that this calcite precipitation here was a result of photosynthetic activity. So that's on the surface, though. That's the thing. But as soon as you break apart the microbialite and look even just a couple centimeters into the structure itself, that sort of enrichment, or those enrichment values, disappear. And we're not actually seeing a preservation of those enrichment values. Now that could mean several things. That could mean that the actual initial formation mechanism for the carbonate itself was not what we're seeing in a modern sense. So all we're getting is a modern snapshot of the mechanisms driving carbonate precipitation on the surface of the microbialites. Or there could be other things such as dissolution and reprecipitation happening, which is actually changing or altering some of the isotopic signals we're seeing. And this is some other work that I've been doing, just collecting a whole lot of values, which once again confirm that we're just not seeing those enrichment values within the structure itself. So this is interesting and something we'll be working on over the next couple of years to understand in a more refined manner. Now, as I said earlier on, as we descend into the lake itself, 22 to 25 meters or so, those balls start to disappear, and the communities start to get, or pardon me, the surface structure starts to get a lot smoother. In fact, below 30 meters, those balls disappear altogether. And you see there's actually a lot of color difference in some of these structures that we pull up from the depths. You get this brown section here, and this is actually not, this is still above the sediment-water interface. Sediment-water interface is below here, and then there's this green component on top. We also brought up some samples from using the deep workers from about 150 feet and deeper, so between 50 and 60 meters. And these microbialites that were brought up were also very dark and brown and didn't actually have any of that green component associated with it. And so if you just take a look at that surface crust associated with the green portion of these deeper structures, you see that within this crust itself there are communities that are associated with it. And as I mentioned, what we're doing now is really trying to do our taxonomy and see what's there and see what's changing over time. The folks from McMaster also looked at biomass and cells per gram, and what they found is that from the surface, going deeper into the lake itself, there is a decrease in the biomass component associated with the surface of the microbialites themselves as well. So the communities seem to be changing overall as we decrease, and there are several lines of evidence that are supporting this. Now, looking at the photosynthetic activity associated with microbialites, this is a structure which some collaborators from actually Dale Anderson, who's here at SETI, and also Ian Hawes, who's in New Zealand, they used a PAM fluorometer to look at PAR, photosynthetically available radiation for the organisms living on the microbialites themselves, and looked at it from different angles. And what they found is that there is radiation available, but what's interesting is that from the top to the bottom, the photosynthetic, the electron transport rate actually decreases. So it's actually getting darker, and there's some shading there. But the other thing that they found is that there is, there's still a lot of biomass associated with both the green and the brown sections of these particular structures. So the brown is not dead or replete of any sort of organisms on the surface at all. And in fact, what's interesting is that there's still some photosynthesis happening down in this brown section, but the organisms that are living there seem to be much more, I guess they're much more adapted to lower light levels or lower radiance levels than the ones on top. The other thing that they found using some infrared imaging is that you can really see that this is the green section here and this is the brown section here. And the calcite minerals really come out in this image on the green section, but not so much in the brown. So there are running hypothesis is that, in fact, there may not be as much active calcite generation in the brown section as there is in the green, where, in fact, there's more light reaching the microbialite itself. And this is another image that they took showing absorption by pigments. And then in fact, this is once again, the green, and this is the brown. And there's still absorption happening. It just seems like they're happening at different rates. And also, it gives you a sense, once again, that the green section is much more active in terms of calcite precipitation. Here's a lovely thing that they did, Dale and Ian, which is absolutely hilarious to us. We've been diving and doing submersible trips during the daylight when you'd think, most people would do work. But they decided to do a night dive, and what they found is that the microbialites come alive in a very different way. What you see here are some caddisfly larvae and some images that were taken at night when they went out, I think around midnight. And what they saw is essentially what I said, is that all of the microbialites really just started to show a lot of grazing activity at that point. There were snails, there were caddisfly larvae, there were other organisms that came out from their little holes and crevices within the microbialites and started showing their activity level then. And so one of the lines of interest that we have now is actually investigating the role of these grazers on the macromorphology or the gross morphology of the microbialites themselves. And there's a master's student soon starting with us on that. But what this really says is it kind of opens up a new venue for us, and now we should actually be there doing night dives and submersible dives and exploring the lake, not when it's convenient on our time, but rather when the entire lake is sort of evolving. So it really was a very interesting find. And these are some interesting, these lineations here, or these stripes, show you some feeding traces, or what look like the remnants of where a snail has gone in and sort of munched its way through a microbialite. So one of our working hypotheses is that, from the shallows down to the deep, there seems to be the same sort of microbial communities, only they get simpler and simpler, or less diverse, I guess, as we decrease in depth. And this may be as a consequence of the organisms that are associated with these communities being more attuned or less attuned to higher or lower PAR levels. So we're actually going to be looking at this closer in the next couple of years. So the next transition that I wanted to talk to you about is this biological to the physical. So we wanted to take a look now at the shapes that we're seeing there, take all the other research we've been doing on the limnology, the research that's being done, as I just showed you, on the biological component of things, and relate this back to the bigger picture. And what we found over the years through sonar work, through a little bit of diving now, because the lake is so large, or so long and so deep, and we're at nearly 3,000 feet elevation, we couldn't dive a lot of this lake effectively in a safe manner. But we did have indications that most of the lake had microbialites in it. And so we needed to find a way to actually explore. The other thing that we found actually in 2005, I believe, is using an ROV. There were some indications through sonar that in fact there were deep mounds between 50 and 60 feet where microbialites existed. And we thought that they petered out or between 30 and 35 meters, where the light really started to peter out. So at this level, the light is at 1% of the PAR levels that you get in the surface. But there's still light coming down at this depth. But nevertheless, what's interesting is we just didn't expect to find them at this depth, and we did using these ROVs. But once again, we're just scientific divers. We're not commercial divers or anybody that's rated at a high degree that we can get down there with any safety or effectiveness, really. So we had to find a way to explore these slowly. We wanted to actually sit and sort of synthesize our environment. And this is another snapshot of these deep water microbialites. Once again, I mentioned to you that they have this dark coating associated with them, which we're finding consistently in any of these dark microbialites. And they're all sitting on top of mounds. They're never actually on the flat regions. And this was entirely unexplored. And so, in 2008, I sort of shared my punchline at the beginning, but really, coming to it now, we had the deep workers kind of enter into our lives. And this was the confluence of a lot of different activity. And we also have the industrial partner, Nuco Research, that has given us a lot of support over the years. And Nuco is the company that designs and builds and basically runs these submersibles. And so this is a submersible in action. It's not very big. It's just slightly over 2 meters in length. And the way that it was built is really interesting. It was kind of an experiment in whether or not you could build something that would be very usable. And this submersible drives like a sports car. I mean, it's very, very responsive. It's small. You can do loop-de-loops. Like, I should probably not tell you how much fun it is to drive. But just to back up, I wanted to tell you that there are 6 of us that in '08 learned how to pilot these subs. And these 2 women here, Rebecca Shepard and Allison Brady, are both students. And we felt very strongly that we should have a student component in. This is a professor from McMaster, one from University of British Columbia, and there is our intrepid astronaut, Mike. And that was a really fantastic start. And this year we had 4 more people learn how to pilot the subs, and 1 that was already trained up joined us as well. So in opening up, or pardon me, in the goal of mapping the lake, what these subs did is it opened up the depths and the extent of the lake. We move typically at about a knot, which is slow, but if you consider that within a 2-week period we can have 40 flights, that gives you a lot of time underwater. And we fly these subs usually for about 3 hours at a time. So each person is in there for 3 hours. And what we have in terms of our data collection mechanisms, our primary data collection mechanism that we all decided we have to abide by is the human component. So no matter what, that is the main data collection mechanism. And within the sub itself, we're recording voice so that you are constantly narrating what you're seeing. So it's a real practice in kind of rubbing your tummy and patting your head. We have this manipulator on the front end here with the claw that enables you to pick up structures. But what we learned in 2008 is that because the structures are so fragile, to go in with this large footprint and try and sample on these very steep slopes was very difficult to do without destroying some of the environment around it. So we actually put a cap on that, and instead, because now we're able to have very high resolution, like sub-meter kind of positioning underwater, we will actually call up what we call event points where we want to go back and sample if you're within a diveable range. If you're outside of that and you're deeper, about 50 to 60 meters, then what we've done now is we actually survey areas, and then as a team we come together and make decisions as to where we want to go and sample these deep structures, and then the deep workers will go in subsequent to that. So we're very strategic and very disciplined about how we sample. On the front end of the manipulator, what you see here is an HD video camera, and we've generated about 256 hours, I think, of HD video from 2 years of flight, so 80 flights. So that's a lot of terabytes of data. And as I mentioned, these submersibles have allowed us to extend our bottom time. You can stay in these subs, if all else fails, which you hope you never get to, for 72 hours. And that's just playing with a lot of the onboard systems. And it increased our range because we could go for 3 hours. We could actually cover a lot of range, and increased our depth. They're actually rated, I think, to 2,000 feet, but the lake is only 210 feet, so we're well within the range of their working capacity, and it increased our safety. So we're working at 1 atmosphere here. You could, even in that year that I was pregnant, I could have theoretically gone into these subs and worked, but
3 meters?
Nope.
210 feet?
Feet, exactly. Yep, exactly. And so it was a wonderful mechanism that allowed us to actually open up this lake to our investigations. So I want to show you a quick video here. It gives you a little bit of a sense of what it's like to be in these submersibles. These are some microbialite fields. These are in the shallows. And I believe this is a sub-to-sub video here showing the sub actually flying and maneuvering across some of the microbialite fields. And in the next image here, this is some of the HD video that's come back. And so what this has allowed us to do is gain context. And as I mentioned, over the years, I've been diving the lake. And when you're in diving, it's a very, very different experience than sitting in the comfort of a deep worker submersible. What you can't see, that's me, is that down there I have my cookies and my water. And so I have my cookies, my water, and my iPhone sitting with me. And the iPhone works great, even with the moisture. It's fantastic. But you're very comfortable. And so what that affords you to do is do field work the way that you would do it, sort of on land. That's Mike Gernhardt there. I'm being very astronaut-like and happy. What I mean by that is, if I'm doing geological field work, say, anywhere, like in the Arctic, I can stop, I can take a look around, I can have a drink of water and think about what I'm seeing, and then perhaps alter my thought about the environment, maybe my sampling protocols and so forth. when we're in there and we have sonar and we have only diving to our disposal in terms of making decisions, that changes the game a lot. And so with the addition of these subs and the context that we've gained, we've actually made a lot of subsequent decisions in terms of the measurements we want to take, in terms of our understanding of the relationship between the microbialites and the physical environment. And I'm going to show you images in a couple of minutes. But I'm not going to show you the other movie because it never works and it crashes my system. But it's really afforded us kind of a new lease on our understanding of this lake. So this is an image here that shows you some of the scientifically relevant exploration tools that we have put into the lake that we've chosen as a consequence of those sort of 4 guiding principles. And then once again, that's the AUV, or the autonomous underwater vehicle, that the diver is beside. So what have we done with all of that HD video? I'm very, very proud to say that we've already analyzed a lot of it, and we did that in the field. And what we wanted to do with that data is to actually morphologically classify the microbialites that we were seeing there. So we could take a look at trends throughout the lake by depth and their association with other physical, chemical, any other parameters that we've measured to date or that we want to measure in the future. So this is a morphological classification cue card, is what we were calling it, that all of us became very familiar with over the course of the field program and subsequent to that as well. And this is based on some seminal work that was done in the late 60s by Hoffman, actually someone in Canada as well, who developed a classification scheme based on ancient stromatolitic structures. And so we used a lot of the jargon or the classification verbiage that you see here while we were describing what we saw in the sub, and then subsequent to coming up to the surface and all that HD video was now available to everybody, we had students, we had the cook, we had everybody sit down, learn these classification keys, and go through and classify all of the structures that we were seeing in front of us. And this was a very, very hard thing to do. It took a lot of time. But what it showed us is that essentially, with a lot of motivation, and I think with a lot of peer support, you can get a lot kind of analyzed in terms of that kind of largeness of data even before you leave the field. So now the interest that someone like Mike Gernhardt has in this project relates to the fact, once again, that we are using this pressurized environment here to explore in a hostile environment. And of course, it's easily relatable to something like this lunar electric rover, which will essentially afford folks to do, the capacity to do the same thing on the moon. But the other, besides the kind of physical comparison between these two technologies, the other thing to keep in mind is that we have a human observer in there who in some cases is a very seasoned observational scientist, in some cases is becoming seasoned as a consequence of them being a graduate student, and in some cases has never done it before, like in the case of Mike. And whoever you put in this particular LER, it would be really nice to know that they've had practice and they've had experience in doing things, not just driving the submersible, but in also doing observational science in a bunch of different relevant places on the Earth. And that's something we started to do at Pavilion Lake, is beyond the integration, beyond the fact that Mike does the dishes and drives the submersible, he does more than that. He spent time with us learning about this kind of basic limnological principles, about microbialites. He knows that classification card inside out and backwards. He's gotten to a point now where he's providing us with so many insights that it's actually shifted some of our ideas and our lines of thinking and our lines of investigation overall with the project. So it's a wonderful case study, I guess, to show that it is a very powerful thing to empower someone with that capacity, such that Mike is not a visitor, he is not a proxy scientist, he is a scientist when he gets into the sub. And this is, I have this whole story that I've actually done for kids, a story about astronaut Mike, and how he does the dishes and he does all these wonderful things. And it's true. And this is Mike here, and sitting and taking part in one of our daily discussions, which became a very powerful component of our day. And this is where we made decisions, where we changed our minds on things, where we argued and so forth. And we did this, within the field, and it really helped us in terms of our planning and so forth, and on the back end as well in terms of what we want to do in the future. These are a few words that have been drawn from a paper that we've just got accepted into planetary space science regarding the construct of a program that will help to, I guess, foster an observational scientist and the capacity to do observational science in our future astronauts. And we've designed what are called learning design principles. So certain principles you'd want to adhere to as you go about this training program. And the last one here is something which certainly is very important. And this is about providing a social experience for this learning endeavor. And what I mean by this is actually providing a sort of collegial environment in which everybody's open and sharing. We found this to be very important. And it seems simple, but in many ways, sometimes even in an academic setting, it's done by grading, it's done by kind of a very different transfer of knowledge. And so we wanted to make sure that everybody in the room was on fairly equal footing in terms of the capacity to exchange knowledge. I'm going to skip through this slide here. And I just wanted to tell you about more of the exploration science as well, and how this helped us to drive the science that we wanted to do with the deep workers. Now, in 2008, we had all of our data go to a tape, essentially. We didn't have the capacity, we didn't have the money to go to a hard drive. And so all of that video data had to be copied and digitized and so forth, and it took forever. And the thing that it did to us is it did not allow us to view tape at the end of every day and to talk about what we saw. So we had folks coming up saying, okay, I was in this trench and I saw all of these red microbialites, and somebody else said, no, you didn't. And then that went back and forth, and that was ridiculous and such an intense waste of time. And so what happened in 2009 is we were afforded the ability to have the tapes immediately go to a disk, and we were able to bring them out and within 2 hours process them and have the capacity to sit together and review them. We reviewed them to make scientific decisions. We reviewed them for traverse planning. We reviewed them as well because none of us are expert submersible pilots. And so there was lots of stuff that each of us was doing that was right and a lot of stuff that was wrong. And we used that time together to say, okay, you need to improve on this aspect of your observational science. You need to give us more context to pull in to use that technology to the best of its capacity. And so that's what all of this flight planning and data synthesis really helped us to do. So we spent hours before the field getting ready, planning all of the different points we wanted to go back to based on what we learned from 2008 and based on some of the outstanding questions that we had. This is an example of a flight planning card where we knew there was this entire section here in the middle of the basin that we hadn't flown in 2008. And it's embarrassing, but I'm going to share this story. We decided not to fly this deep section of the lake because we had a few passes done by the AUV, and it looked ridiculously boring. And so because all of us were so overextended, we just decided no, none of us wants to do that monkey work. But then what we found is that there were some little indications from some of the data, the sonar and also from the AUV imaging, that told us that there might be something interesting there. And in fact, there was. And so we had several of what we called lawnmower pattern flights planned. And the big joke was that if you didn't contribute to the planning, you got stuck with these. But they turned out being some of the most interesting dives because there are deep mounds throughout the central basin here, which in many cases are very large and are replete with microbialites. And so those are major finds for us this year. Through the flight planning, we generated all of these traverse data sheets here so that before anybody showed up into the field, if they were doing a flight, they had a binder. So it was very highly organized and choreographed. You had a binder that you would flip through that would give you information, would give you lat long points, it would show you your track that you were supposed to fly. So all of that came together and enabled us to be very choreographed, as I mentioned before we got into the field. So I'm going to fly through some of these here because I wanted to show you a little bit of an image that will kind of represent the change between 2008 and 2009. And this is an image from 2008 at the lake where we were sitting in the basement of one of the local residences. And this is like basically 24/7 we were copying tapes. And this is all of us just crowded around on the shag carpet here trying to have a conversation. And then as a consequence of some wonderful funding, both from the NASA MAMA program and the CSA, we were able to bring up this communications trailer this year. And that's totally how we roll now. And so very different, and we were able to have those dialogues like you saw earlier on. The other thing that we implemented this year was some communications changes. And so we always had through water comms with the submersible, but what we didn't have beyond that, it's push to talk, is the capacity to synthesize that data as I spoke to you about. And now we were able to do this. We had folks from NASA Ames actually sitting on board of chase boats and synthesizing the data in real time using an interface that I'll show you in a couple minutes, and then building a Google Earth map in real time of our track, of our depth, of the images we were seeing, and some of the video clips coming off of that as well. The other thing we did, which worked towards the back end of our project, is we were actually able to stream our voices from the deep all the way to the surface as a consequence of the work of some folks from NASA KSC, Mark Siebert and Mike Downs. And that, for the first time, allowed everybody to hear what was happening down in the depths and all of the observations that we were calling up of notability. And in the future, we'd like to try and move that such that we're able to get voices two ways and actually see if having a science backroom team would actually be of some utility to our operations as well. So we're going to do that sort of maneuvering when it comes to our ops as well. The other kind of operational end of things in terms of the science that we've been doing is metrics. And so we've been measuring, or trying to measure, or start some work on whether or not we can be scientifically efficient despite the fact that we have a lot of these physical constraints in terms of life support and other constraints in terms of battery power, consumables, and so forth on our lives. And so we've been using, we've been developing with Mike Gernhardt's team things such as traverse objectives and science merit scales, and allocating this to all of our different traverses. I'm going to fly through these a little bit, and then we can talk about these later on because there are a lot of slides here, and I know I'm running out of time. But we did everything in terms of metrics, ranging from looking at the scientific merit of a traverse and the post-scientific merit of that traverse. So what would you say? Were you actually going to go out and test a hypothesis? Did you do that? And we gave those assessments afterwards, and we'll do that again in 2 years. And we also looked at things related to human factors and the interaction between humans and human and technology, and our workload factors and so forth. This is a Cooper-Harper scale that we use to actually look at how much you were compensating for your technology at any given point. And the other component to our understanding of scientific efficiency was came to data quality. So how good was your data quality? Did you actually film something well or not? How did that influence your science? And actually, one thing I wanted to show you was this is the fatigue sheet that all of us had to fill out. So we also measured fatigue. And one funny kind of phenomenon is that a lot of people would go into the subflight, between a 4 and a 5, and they'd always come out a 3. And that was always a consequence of adrenaline just kind of coursing through everybody's system and making everyone feel pretty good for a little while. I've spoken about the surface data systems and this capacity this year to generate in real time a map of where we've been and what we've been seeing. This is a static image of that capacity. So what you're seeing here is a cute little submersible icon, and these are the tracks that the submersible generated. And then if you were to click on any one of these little envelopes here, a static image would open up, and then a quick video or video clip of what you saw there was generated as well. And so all of this data has now been synthesized. And the way that we enabled that is we had the sub and all of that data coming to chase boats up on the surface. And there was a science stenographer putting that all together. And so let's see, let's just move forward here. I can talk to anybody who wants to know a little bit more about this after the talk, but just so you know, there was a very simple but very effective interface that Matt Deans and David Lees at Ames generated that allowed them to, every time, they're not experts on microbialite morphological classification terms, but we had this generated, and any time we would call something up of notability, they would click on one of these buttons, and all of those notes would get generated, and then any other subsequent event notes were generated as well. And we found it very, very helpful to the science that we were doing. And this is an image here of Matt sitting, and this is the navigator at the back, and their computers are talking to each other, so that all of that USBL and all of the acoustic communications were being recorded by Matt as well. So these are a few slides that show an example of how this worked in some circumstances. It worked such that we were able to even change our flights, just the next flight over, because we got information from the pilots. It was synthesized very quickly, and we were able to say, okay, this is an interesting place of target. Now let's go and visit that, and let's reprioritize our entire day so that we could go to those particular sites. And the other thing, as I mentioned early on, that it did is it enabled us to have really productive conversations at the end of the day. So instead of just a he said, she said kind of scenario, now we had video, we had notes, you could compare and contrast everything that everyone saw. I'm just going to go and skip forward on these a little bit here. This is an example of some experiments we did in terms of sampling procedures and collecting rocks. The other thing that Matt and his team did is he generated this, once again, this very simple but very effective way to look for and to compile all the data that we had. He's going to be improving on this over the years. And this, once again, just sped up and made us much more efficient in the field in terms of comparing notes. This video I can show you guys later on, but the last thing I wanted to tell you about is this. Is that, as I mentioned, we did a lot of morphological classification in the field this year. Just of the 2009 data, there was 156 hours. These are some students that really were the backbone of that, of those activities. So what we found, these are some still images from the submersible flights that we did not have the, I guess, the contextual capacity to appreciate before, is that slope and also some of the lateral topography in the lake itself really makes a big difference in terms of where the microbialites concentrate and where they don't concentrate. So these are actually, this is a topographical high, and this is a trough here, and once again you see a high. And we got at this particular physical pattern as a consequence of the submersible flights. The other thing that the subs helped us to really document are unusual microbialites, or shapes that we hadn't seen before, so like this long, skinny kind of banana-like shape. And the other great thing is that after our field season in July, I went back about a month later and dove many of these sites, and because of the accuracy of our coordinates of our tracking system, we were able to almost put ourselves right on top. And then I could go in, and we have now some growth plate experiments, some sediment traps in some of these interesting places that we identified with the subs. The other thing that major discovery with the subs that we made is that there are some very big microbialites in Pavilion Lake. This one here is a microbialite which is at 87 feet at the top, about 102 feet at the bottom here, and the circumference is, I'm going to intersperse between feet and meters because of diving and so forth. It's 13 meters around, so it's very large. It's almost 45 feet around. It's a very big microbialite. And the position of this structure is such that we would have never caught it or thought it was, at all in diving, because on sonar it just kind of showed up like a big rock. But we didn't realize that this structure was there. And what we found is that all of this microbialite is actually growing on a large fallen boulder. And what this started us thinking is that rock substrates are in fact a very important component of where the microbialites are nucleating. So this was a wonderful end member and a very interesting find unto itself. And this is another example of some really, kind of weird fabrics or gross or kind of mesofabrics of microbialites that we're finding on fallen rocks itself. And these are all images that have come back from the submersibles. And we're finding those same fabrics now on some smaller rocks itself. And the other thing, once again, coming back to this influence of the physical on the microbialite, distribution, is you see that they're kind of in steps, and we're seeing that throughout the lake. Microbialites are associated with slopes, not with where the lake shoals at all, where it actually flattens out. We don't see any microbialites. And that plays back into this idea of sedimentation rates being important in this lake, and we think that their location is also tied into sediment accumulation points. We also found, many of you know Imre Friedman, and he visited the lake in 2004 and thought that, I can't point, but there are these interesting, what he thought were green algae throughout the lake, and he thought they were important nucleation points for the carbonates throughout the lake, but he never had a chance to come back and visit the lake and investigate these more. But we've actually started down the path of looking into these with more rigor, and we're finding that they're everywhere, and they tend to be associated in the shallows, but also with these chimney structures, which is pretty interesting as well. And we found those with the sub. And the chimneys are very curious. One thing I didn't mention is that if you cut them in half consistently down the middle, there is a channel, and it's usually infilled with some very fine calcite. But we've tried every which way to Sunday to actually measure groundwater flow or track any sort of groundwater flow through them. They look like flow patterns, but we haven't been able to track anything whatsoever. That doesn't mean that because they're not active now, they haven't been active in the past. But we don't actually know why it is that the chimneys are there at all. We thought they were associated with groundwater input areas, but it doesn't seem exactly to be the case. And we're finding them as a consequence of the subs in very different depths than we first expected. Once again, these are some, oh, this is really horrible. Sometimes you'd go down and then, you know, when you were out of range of coming up to the surface, you'd find you'd have a mosquito or some sort of fly or something, and that would screw up all your video. But from this picture, you still get a sense of the fact that there are some weird transitions in the lake itself. This is a trough, topographical low. This is a high where you get the concentration of microbialites. And this is infilled here with you know, green slimy stuff, which we've put some of it under a scope, and it looks like it's green filamentous algae, but this is yet to be confirmed. The other thing that the subflights showed us are these very strange, what we've termed microbialite roads. These very straight, very kind of limited, concentrated microbialite sections. And this is actually looking upslope. So these tend to start at about 130 feet and go all the way up to the surface. This is another image showing a very clear delineation in terms of some sort of transition here between the microbialite and the algal component. This is a slide from that I just data dumped about a bunch of operational lessons learned, which I'd be happy to share with you later. But I'm going to end here, as I'm sure I've gone over my time. And I just wanted to, first of all, thank all of our funders at the CSA and NASA, and also our previous funders. And this is a bit of humor that, you know, our Canadian humor. We've put bumper stickers. Actually, I think it's more Californian humor, really. We have all the bumper stickers on all of our subs now. But thank you. Yeah, so that's one. The other one says, protect the herms, which is this central mound in the lake, which we find very interesting. But anyways, thank you so much for coming out, and I'd be happy to field any questions now. Thanks.
Hi, Darlene. Great talk, thank you.
Oh, thanks.
So can you speak to the growth rates and the guessed ages of some of the different forms that you saw?
Yeah, that's great. Thank you for that question. So the question is about the ages and the growth rates. So they were initially, the growth rates in the first paper in 2000 was estimated at about 2 centimeters per 1,000 years. So slow. But the other thing about this lake is that we know it's a post-glacial lake. So it's probably between 10 and 11,000 years old. So if you do the math, and then 2 meter tall microbialite, that doesn't quite make sense. But then some of the other work that the McMaster folks have done using C14 has raised the growth rate to about 5 to 6 centimeters per year. It still doesn't quite, oh, I'm sorry, per 1,000 years. I'm sorry, yes, thank you, per 1,000 years. But nevertheless, that still doesn't, like if you assume a constant rate of growth, it still doesn't quite make sense. So probably there's been an inconsistent growth rate that's happened, or sorry, a growth rate which has not been consistent to that degree. And that's something that we're trying to figure out as well. But yeah, but we know that the lake is post-glacial, and so that helps us anyways constrain the time period of growth. Thanks. Yeah.
You refer to these things as communities, I guess. Mm-hmm. But in principle, they could be kind of organisms. Is there any evidence for either communication of information within the entity and or like specialization that yield resources that get there?
Yeah, that's a great question. We actually have a student who started, but unfortunately she stopped looking at cell signaling components in terms of the surface communities and surface organisms on the microbialites. So I can't give you an answer beyond that because she has to restart There's a variety of things that happen, but she's at Washington State University, and hopefully she'll start relooking that. But that's a really good question and something that's come up kind of internally again and again. And we're hoping we'll get some sort of understanding in terms of, overall, I guess, communication. Yeah. Thanks.
Is it too soon to say if many of these algae are in fact cyanobacteria? Your
No.
website talks about these multi-billion-year-old organisms.
Yeah.
But it sounds like they might be the eukaryotes, the regular red or green algae.
There are eukaryotes for sure, but on the surface of the microbialites, what we're primarily seeing are cyanobacteria. So, and in fact, there was some work done by a PhD student, she should be finishing soon in Hong Kong, and she's shown that the bulk of the biomass on the surface of the structures is bacteria. So, but then, the entire lake ecosystem is much more complicated than that. So it kind of depends on what scale you're looking at. But yeah, that's a great question.
This AUV, it's autonomous in what sense? How does it operate?
You can program it to fly at certain depths and do certain transects, and it will basically go about and do that for you and make certain decisions based on obstacle avoidance and so forth.
Can you change its trajectory, or once it's launched, is it on its own?
That's a great question. I don't know the exact answer to that because I have seen it have accidents. And I'm not sure if there was manual kind of, or there was an intent to manually override that and it just didn't come in time or not. But as I understand it, that's actually quite hard to do once it's actually out doing its transect.
Have you considered a technique like what Craig Winter did with his yacht, sampling different areas and just doing a scattershot DNA?
If you've got a yacht, I would be happy to talk.
No.
I didn't even show you the video on how we get those suckers in the water. No, yeah, you're kind of talking about kind of mass scale sampling throughout the lake. You know what? What would be really, I think, effective to do without just like pulling up a whole bunch of these protected structures would be to take one large one up and do a coordinated sampling on that. And we're just writing a proposal to exobiology to do just that, but in situ, because we haven't logistically figured out how we would ever investigate one of those 2-meter structures, bringing it up and so forth with the resources we have and the time that we have and so forth. There are a number of things. You probably have to do that with divers. It would probably take some time. It's cold water, it's altitude. So there are a number of things that we're kind of limited by. But with the right technology, you should be able to do that. And there probably would be a very interesting thing to do, because one thing that I didn't mention here is that when you bring up the structures, a lot of them tend to have an anchor to them, or what we're calling an anchor, a gray sub-component to them, which is below the sediment-water interface. And we're interested in the organisms there and whether or not all the structures have that. So yeah, it's a good question. I don't think I'd ever want to mass sample, but certainly sample a big one would be very cool to do. Yeah.
Thank you for this deep peek. 2 quick questions. First, is the lake protected now from other macho divers?
It is. It is. It's actually now part of the British Columbia Provincial Park System, which is great. So the basin itself is protected as well, and there are certain areas that are open for public diving. And actually a part of the project that has been really wonderful to see, I guess, applied is that as a consequence of all this data, there's now a kiosk, an educational kiosk that's been put up, and they've used our data and our images and so forth. And you see a lot of traffic going through there. People are interested in what this lake is. And by and large, especially the local residents, people are very interested in protecting the lake. So it's a wonderful course change, really. It's a consequence of science. So.
Now, it seems this work is a very strong advocate for manned exploration. But given the budget realities, are there lessons that one can learn for robotic missions?
Yeah, that's a very interesting question. In terms of robotic missions, I guess I'm limited in my scope of imagination, because so much of the time we use our robots for recon and to see what's there already, and that's what we've done here as well. But what we wanted to do this summer is actually to get at that question in a better way, in a more quantitative sense, is we ran an experiment where in the South Basin, where we know the springs are coming in, where we have a CTD attached, conductivity temperature depth meter attached to the AUV. And we ran it into that, we didn't physically run it into, sorry, I should use better terms. We flew it in that region to measure conductivity changes coming from the spring outwards into the basin itself. And then on top of that, we put in the submersible with the CTD on it as well and ran that same mission to see what the difference in terms of quality of data coming back would be and ease of data collection as well. So, you know, I'm probably sidestepping the question a little bit, and that I don't really know the answer. But I think that the best answer I can give is that there's a lot of unexplored territory in terms of how we utilize robotic missions to support and to, I guess, anticipate human exploration as well. And I think we haven't even scratched the surface yet of what we can do. So, thank you.
Darlene, I was wondering if you've seen any larger predators, like fish, attacking the surface of the microbialites.
We don't. The fish are stocked. So there are fish in this lake,
okay.
and I know where all the big ones are because of the subflights. It's wonderful.
Yeah.
But they're stocked in this lake. But they must have some sort of, they must have had an impact for sure, because the fish in there are the top predators, and overall in the ecosystem of the lake, there must have been some adjustment. We do see them certainly, congregating in areas where the streams are, or where the groundwater is coming in, and they're probably affecting that region more than anything else. But we have not actually noted them, even in close association with the microbialites themselves, which is kind of interesting.
Yeah. And also you mentioned that you're seeing diminished diversity with depth.
Right.
Can you say the same for long axis as you move away from?
Yeah. That's a great question. No, we haven't seen that, but what we have seen is a statistically significant difference in the, let me just make sure I get this right. I think it's the bacterial diversity between the east and the west side of the lake in the central basin. And this was the work done at University of Hong Kong. So not by depth, not... Well, there's not a huge difference because of the steepness of the canyon. There is a little asymmetric nature to the canyon walls, but both sides of the only difference is outside of light is that on one side there's a road, and there's been a lot more recent kind of damage or infilling in that area compared to the other side. But we're not exactly sure what the major difference is. Qualitatively, there seems to be a slight difference as well when we look at the east versus west, but that was kind of an interesting recent find as well.
How does the diversity you're seeing compare with other microbialite communities in other lakes?
In the area?
Just globally, if you've looked at that.
That's interesting. Well, we're not finding anything unusual, I guess is probably the best thing I could say. And in terms of quantitative comparison, I could give you an exact response to that, but I can tell you that for sure we haven't found anything unusual yet. Like in the surface communities, we're seeing things like oscillatoria, calthrix, stuff that you find everywhere. So that's an interesting question because, and what will help to supplement the answer to that is the work that's being done that I haven't showed you in the Caribou Plateau, which is nearby, where there are all these highly alkaline, like pH 10, saline environments where you get these laminated microbial mats that have carbonate precipitating within them, but not forming up into these shapes. And so what the organisms are there compared to what we're seeing here will be interesting as a comparison point. But, yeah.
Darlene, what happens over winter? What sort of, the lake doesn't ice over, does it?
It does, yeah, it does ice over, yeah. And we've dove in the lake before. In terms of seasonality and of changes, there seems to be less variability between, let's say, February and July than there is between the spring turnover period, which is in April, compared to July. So during the winter there is ice, and it's actually, there's a lot more sediment that's kind of coming up in the water column at that time of year too. But aside from that, we haven't seen anything else dramatically change between the winter and the summer period.
Although the ice wouldn't be as thick, I don't know how thick it is, but it might be a good analogue for Europa and exploring
Yeah,
European
people
oceans.
brought that up in terms of technology development within this lake and doing science in an environment whereby you have fragile structures and so forth. That's a great, I think that's an A step right there, right? But it has to be the right technology and so forth. But you couldn't put anything really that hasn't been well vetted, I guess, in this lake before. And that's the one thing that really pushed us towards a submersible. It's been flown all over the place. We knew that, like the text told us from NUDCO, anybody can fly the sub within a minute. But flying it well is something hard to do. But the great thing is that they're highly maneuverable. And the thing with the AUV is that we had some problems at the beginning, but they were vetting it in other sites that were not as fragile as this, and then got it to a point where they felt comfortable putting it into the lake.